Okay, welcome back to Algebra 1 Honors. Today we're going to talk about Lesson 4-8, rate times time equals distance. And that's something, if you think about it intuitively, you actually already know that idea. And when you get a little bit older, when you get to high school, it's going to be a very important idea because that's where you're going to start driving. You're going to get your learner's permit and then your license. And so the idea that, for example, if you jump in a car and you're headed to Walmart, if Walmart is 100 miles away, if you go 50 miles an hour, it's going to take you 2 hours. If you're a more elderly, cautious driver and you drive 25 miles an hour, it's going to take you 4 hours to get there. But to figure out how far you've gone in your car, if you're going a certain speed, you multiply by how many hours or whatever that you've gone. Okay, so hence rate times time. How fast you're going times how long you go equals how far you get. Now, in distance problems, there's sort of four ideas, four cases. And if you'll keep these in mind, distance problems will be very easy for you. Okay? Now, here are the four ways to sort of think about distance problems. And here are my little pet horses that we're going to use as props here. The first case, the first idea about a distance problem is you might have two horses. Your book sometimes makes them helicopters or bicyclists or runners or whatever, ships or cars. And the two objects, I use horses, are a certain distance apart, okay? And they're going towards each other. They're galloping towards one another. Now, you're going to have the same kind of variables. You know, maybe this is a really speedy horse and he's going really, really fast. And this is a slower horse and he's, trudging along here. And then the horses may start at the same time going towards each other, or the slow horse may get a head start, and then the fast horse starts later. And then you have the idea of the distance. How far apart are they? Okay? So you still have those different variables, but the general idea is that you have two objects, two horses, two ships, two cars that are apart from one another, but they're going towards each other. Okay? Now, and the idea is that when they meet in the middle here, they will have covered the entire distance, because the distance that this horse goes plus the distance that this horse goes when they meet in the middle, or not in the middle because this horse is faster, they'll meet more over here. That total distance of this horse plus this horse equals the total distance that they were apart. Okay? Now down here, this is a slightly different one. The horses don't like each other. So they start at the same exact spot, but they're going different directions. Okay? And again, they could start at the same time. They could start at different times. Okay? And the problem will have to tell you that. One horse can go faster than the other. Maybe they go the same speed. Okay? And one part of that problem will be they'll either ask you how far apart they end up after a certain amount of time, or they'll tell you how far apart they are and they'll ask you to calculate how long they've been running or how fast they each run. You're going to have the same three variables, but the basic idea here is that if they start at the same point, when they stop, when they end up, okay, the distance that this horse travels plus the distance that this horse travels is how far apart they're going to be at that point. Okay, that's the big idea that you want to keep in mind. If they're going opposite directions, whenever they stop, if you add their distances together, how much each one went individually, that's how far apart they're going to be. Okay, that's the big idea to keep in mind there. Now, then there's the overtaking situation. Okay, and we have two horses. It's kind of like an actual horse race. Two horses, and they come out of the gate together, okay? And usually the way that this one is phrased is that there's a slow horse, so that would be me, right? I'm the slow horse down here, the brown horse. And I'm going ker-clunk, 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 and I'm trudging along here. Now, you're the really super fast horse, okay? So I get a head start because I'm an old slow horse. So I go, and maybe I'm all the way out here, and then an hour later they let you out of the gate, and vroom, you start going really fast to catch up, because you're a fast young horse. Okay? Now, what you want to remember about this situation is that, first of all, if I'm the slow horse and I'm going ka-clunk, 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 okay, the only way you're ever going to catch up with me is if you're running faster than me. Okay, so if they give you a slow horse, but this guy's even slower and he starts later, he's never going to catch up. Okay? So, the horse that starts later has to be running faster or he's never going to catch the other one that had a head start. Provided that's okay, then the other thing you have to realize is, I'm trudging along out here, trot, 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 trot. Fast horse takes off, zum, 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 zum. I keep going slow, but he's going faster, 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 and he catches up with me. Now, when he catches up with me here, okay, the thing to look at and realize here is that although we started at different times and we went different speeds, when the faster horse catches up, we're the same distance away from where we started over there at the beginning. Okay, that's an important idea. So when Mr. Fast Horse here catches up, we're the same distance. Even though it's taken me longer to get here, we're the same distance from where we started. Okay, so his distance will be equal to my distance. It's just if he's going faster, it's taking him less time to get there. And then down here, and then you have the idea, and I don't know why they throw this one in. They seem to think it's very complicated, but this is sort of a duh for me. A round trip. Okay, you're going to assume in problems that are a round trip that the distance out to where you're going is the same as the distance back to where you're going. So the problem might say, you know, you're skiing up a mountain, and then you ski down the mountain. Well, the assumption in the problem is it's the same distance up the mountain as it is down the mountain. Now, in reality, that might not be true, but that's an assumption in distance problems, that a round trip is the same distance out as it is back, unless they tell you something different. Okay? And you need that information to solve the problems. All right, now, so those are the 4 cases. We're going to look at 2 of them. Okay, we're going to look at the first case where we have 2, and I'll see if it's what it is in a minute, 2 things going towards each other. Okay, so this case right here. And then we're going to look at the overtaking case. Okay, because these 2 are very similar, and this one, as I said, is kind of a duh for me. So let's look first at 2 things that are a distance apart that are going towards each other. And that is problem number 1 on page 169. So number 1, page 169. And we're going to follow the same series of steps over here. So first of all, we read the problem. It says, at noon, a private plane left Austin for Los Angeles, 2,100 kilometers away. Okay, so the first thing I'm going to do is I'm going to put Austin here and Los Angeles over here, just as dots. And it tells me that those 2 cities are 2,100 kilometers away. So this distance from here to here is 2,100 kilometers, okay? And it says in that first sentence that a private plane, okay, is leaving Austin to go to Los Angeles. So I have a plane here. It's leaving Austin. Okay, and it's headed this way. It's going this direction, towards Los Angeles. That's my private plane. Okay, now let's see what else it says. It says, then I also have a jet. Oh, a zoom, zoom, zoom aircraft here. A jet leaves Los Angeles and heads for Austin. Okay, so I have a jet that starts over here. There's this turbulence there. This is a jet. He's going that way. Because he's much faster, I think. He leaves Los Angeles headed towards Austin. Okay? So now, I should be thinking at this point in time here, based on my 4 cases, that somewhere in here, not in the middle perhaps, but somewhere along this flight route, the jet and the private plane they're not gonna collide, hopefully, but they're gonna meet one another, okay? So, the distance that this guy goes and the distance that this guy goes, at some point when they meet, those 2 distances added together are gonna be 2,100 kilometers, okay? That's just kind of intuitive, look at the picture, think about that. All right, now what I'm going to do is I'm going to create a chart to organize my information. So I got my picture, now here's my chart. And remember I told you before that almost all of our charts are going to have 3 rows and 4 columns. Well, guess what? This is another one of those. Okay, there's my 3 rows, there's my 4 columns. This is going to be rate or speed times time, how long, equals distance. Okay, and I could actually put it here, R, T, and D, right? And then what have I got to work with? Well, I've got a private plane, P, okay? And then I've got a jet, right? That are the 2 things that I'm looking at. Now, then let's see, we can put our information in here. This is about the 3rd time I've read the problem, right? Which is what you need to do. Okay, it says that the private plane is flying at 500 kilometers an hour. That's his speed. Private plane, 500 kilometers an hour. This is in kilometers, so I'm okay. All right, then it says, 1 hour later, we're going to ignore that for a minute, that a jet left Los Angeles for Austin, and he's flying at 700 kilometers an hour. So this guy's going faster, 700. Okay? Now we got to figure out what the times are. So it says that at noon, so this guy left at 12 o'clock. Okay, 12 o'clock. At noon, okay, and flew. And then an hour later, the jet left. So this guy leaves at 1300 or 1 p.m. Okay? So in terms of time, this guy left earlier, right? And he's going to fly an hour longer than this guy. I like positives, so I'm going to choose the jet's time as my variable t, because then I can say, I know that this private plane, he started an hour earlier, so he flew however many hours the jet flew, plus that extra hour, because he started at noon, this guy didn't start until 1 o'clock, okay? Now sometimes your book will have a minus here. I like to do it as a plus just because I make fewer mistakes when I have pluses, okay? Now, I'm then going to have to calculate what the distance, how far did the private plane fly, and how far did the jet fly? Well, that's real simple, because just like we said with driving a car, if you're going 50 miles an hour and you hop in and you drive 50 miles an hour for 3 hours, you multiply to get how far away you are. 3 times 50, 150 miles. So this is an easy one. 700 times t, that's the distance. Right? So however long the jet goes, if it goes for 1 hour, it'll have gone 700 miles. If it goes for 2 hours, 1,400, and so on. Now this one up here, to multiply, that one's a little more complicated. All right? Now, there are my distances, though, that both of those, the private plane and the jet, will have gone. Now, here's the part that gets most people. Here's where they stall and they go, uh-oh, what do I do now? Okay? So we should also archive over here. The only variable that we needed here is time, right? And it's going to be time jet flew. And that's what our t is, the number of hours the jet flew. Okay? And t plus 1, so the number of hours the private plane flew, at the end, if we need to find that, we'll have to add 1 to that. So now our equations, though, and this is the hard part. This is the part that stumps somebody. Remember what I said in the beginning? You have 2 things that are far apart. and they're coming towards each other, the distance that this guy goes, okay, so if he's blue, he's going to go, and he's flying faster because he's a jet, so he's going to get further, right? He might get somewhere out to here. And then the private plane, right, starts over here, say he's red. He might only go that far by the time they meet because he's flying slower. Right? He's 200 miles or kilometers an hour slower. But when they meet, when I add their distances together, this distance plus this distance has to equal 2,100 kilometers. Okay, that's the part that stumps most students. Okay, so that's where our equation is going to come from. We're going to take this right here, right? This is the distance the private plane goes, and this is the distance the jet goes, and we're going to add them together, and they have to equal the total distance apart that Austin and LA are. Okay, and there's our equation right there. So we come over here and we say, okay, 500 times t plus 1, that's how far the private plane's going to go, plus 700t, that's how far the jet's going to go, and their combined distance has to be 2,100. And then we have to solve. So in order to solve, we have to distribute, right? And we're going to get 500t plus 500 plus 700t equals, make sure you make your t's kind of curly on the bottom so you don't read them as pluses, equals 2,100. Now we're back to those like term things, those same kind of animals. 500, I've got a t here. 700, I've got a t there. I've got 1,200 t in total, plus 500 equals 2,100. Let's get rid of the 500 by subtracting on each side. So I'm left with 1,200 t equals 1,600, and t is going to be 1,600. I divide both sides by 1,200. Okay, so let's do that here. Well, let's see, I can reduce by 100 on the top and the bottom, so that gives me 16 over 12, and then I can divide by 4 on top and bottom. 4 goes into 16, 4 goes into 12, 3. Okay, so my t, my time, is equal to 4/3. Now what does that mean? Okay, because we like it better when we come up with nice whole numbers like 2 or 7 or something. But this is actually a correct answer. It's an okay answer, and it's a fraction. What it means is that it took if we change this into a mixed number, it's 1 1/3. Okay, and it was time. It was how many hours, okay, did the jet fly, right? So 1 1/3 hours after the jet took off, okay, it's going to meet the other plane. Okay? And here's when the jet left. So let's see, so 1 1/3 hours, you could even change it to minutes, right? 1 1/3 hours would be 60 minutes plus 1/3 of an hour, that's another 20 minutes, be 80 minutes, or an hour and 1/3 of an hour. Now let's go back and see what the question asks for. It says, at what time did they pass each other? When did they meet here? Okay, so we have to go back and look and see, okay, the jet started at 1 o'clock, all right, and an hour and 1/3 later, it flew for an hour and 1/3 before it met the other plane. So an hour would make it 2 o'clock, 2 p.m., and another third would make it 2:20 in the afternoon. So 2:20 p.m. is the answer to our question. That's when the planes met. Okay? And now what we should do, okay, is to check and make sure that after flying for an hour and a third, okay, the planes would actually meet there. So we figure that at 700 miles an hour, in an hour and a third, the jet is going to go 700 plus 1/3 of that, okay? And this one's already been flying for an hour, so it's gone 500. It's actually going to be flying for 2 1/3 hours. So in 2 1/3 hours, this plane, because it's going 500 miles an hour, 2 hours it's going to go 1,000 miles plus another third of 500. And when I add those together, oh look, it does come out right. I add 1,000 plus 500 over 3. That's how far the private plane went. Now add that to 700 plus 700 over 3. Well, here's 1,700 right there. Add these two together, I'm going to get 1,200 over 3. Another name for that is 400. 1,700 plus 400. Oh, yes. They've gone that distance of 2,100. Okay? So, a couple of keys to this problem, though, is to remember that these two distances added together, because they're going towards each other, right, add up to the total distance that they have to cover. The other thing, and this is a really sneaky problem in that regard, they didn't ask you how long did the jet fly. They asked you what time did the two planes meet. Okay, kind of sneaky, and I guarantee you on an SAT, they're going to put this answer, and they're going to put this answer. Okay, so you have to go back and read the problem and figure out what is it that the problem wants to know. Didn't want to know how long the jet flew before they met, wanted to know when they met. So you have to go back and look at what time the jet left. Okay, now let's look at only one more. Let's look at the overtaking problem. Okay, so we're going to reuse our sections over here. And we're going to reuse our table. And we're just going to put different information into our table here. And it's probably not going to be a jet and a private plane. And it's going to be problem 2 on page 169. Okay? So we read it, and it says, at 8 a.m. the Smiths left a campground driving at 48 miles an hour. At 8:20, so a third of an hour later, 20 minutes later, the Garcias left the same campground and followed the same route, driving at 60 miles an hour. At what time did they overtake the Smiths? Okay, so this is an overtaking problem. Okay, we have the Garcias and the Smiths. Okay, so the Smiths, we put the Smiths here, and we have the Garcias. All right? Okay, so let's do blue here. We'll have the Smiths, and down here we'll have the Garcias. Okay, and then let's see what it says. At 8 o'clock, the Smiths left. So the Smiths leave at 8 o'clock. Let's put our 8 o'clock up there. Okay, and left the campground driving at 48 miles an hour. So these guys are going to go 48 miles per hour. So we can put this in up under our rate there for the Smiths. 48 miles per hour. Okay, this is about the third time I've read the problem. It says at 8:20, the Garcias left, and they're going to go the same way, but they're going 60 miles an hour. Okay, so they leave at 8:20. Okay, but they're going faster. They're going 60 miles per hour. Okay, now that meets our number one criterion, remember? These guys left first. So since they left first, these guys have got to go faster or they're never going to catch up. Well, they are. They're going 60. So they're going to slowly gain on these guys. If they're only going 48 miles an hour, eventually the guys going 60 are going to catch up, even though they left later. Okay, so we know they're going to meet. Okay, and the Smiths are going to they're going to keep tooling along, and they're going to be out here somewhere, right? Some point out here in the National Forest. When the Garcias are going to go much faster, but when they finally catch up, they'll be at the same point on the road. The distance will be the same. So now we've got to fill in the rest of our table up there. So we have to do time. Okay. Now again, I like to use a plus. So since the Garcias started later, and this is the other thing we need to be careful about, it's 8:20. It's 20 minutes. I don't use a 20 because you notice my speeds are miles per hour. So I have to look at that 20 minutes and say, okay, that 20 minutes is a third of an hour, right? Because there are 60 minutes an hour, 3 20s. So if the Smiths, if I have to relate the Smiths and the Garcias here, I'm going to say that the Garcias drove for a certain amount of time, t, because they drove less, they started later. And the Smiths have an extra 20 minutes on them because they started 20 minutes earlier. So that's a third of an hour.
So t plus.
So it's going to be t plus third, because they started earlier, so they drove 20 minutes longer before these guys started. Now, I'm pretty much almost done at this point. This is the hard part. Okay, now I got to multiply. 48 times t plus 1/3. That's how far the Smiths are going to get. And then 60 times t. That's how far the Garcias are going to get. And here's the key to the whole problem. Okay, you have to step back and think, okay, these guys are going faster, so they're going to catch up eventually. Okay? And when they catch up, they've gone the same distance. Okay, so it'd be like me, I'm starting out really slow, and I'm walking, and you're back there, and all of a sudden, zoom, you start out. Okay, well, I might get to here before you catch up with me, but when you catch up with me, we've gone the same distance. Okay, so this distance, okay, I'm not going to add in this case. I'm going to set them equal. This distance and this distance, right, they're going to be equal, because when you catch up with me, or when the Garcias catch up with the Smiths, they'll be the same distance away. So now, my only variable was time, and it's time Garcias drove. Right? So that's what t is. My equation is going to be 48 times t plus 1/3. That's how far the Smiths will have gone. That's the same distance that the Garcias will have gone, 60t. And now I have to solve. Okay, so now I'm going to distribute. And I get 48t plus 1/3 of 48 is 16 equals 60t. Now let's see. I'm going to subtract the 48t from both sides. And that gives me 16 equals 12t. Divide both sides by 12. And that's going to give me, see, I can reduce this. Divide by 4, I get a 4. Divide by 4, I get a 3. Oh, how strange. It comes out to be the same answer. And I get, that's just a coincidence, guys. It's not that the answer is always going to be 4/3. Okay? Now, what do I have there? Okay? What I have is that the time that the Garcias drive, the amount of time to catch up to the Smiths is 1 hour and a third, 1 hour and 20 minutes. Okay, but let's see if that's what the problem asked for. No, it says, at what time did they overtake the Smiths? Well, when did they start? They started at 8:20. It took them 1 hour and 20 minutes. So if I add 1 hour and 20 minutes to 8:20, here's 8:20. And if I add 1 hour, and that third is 20 more minutes, I get 9:40, it was a.m., when the Garcias catch up to the Smiths. Okay?